Alright, in this problem, it's asking which takes more energy to vaporize, 1 kilogram of saturated liquid water at 100 degrees or at 120 degrees. So, naturally, it's asking in a true or false form. Let's find the answer, and then we'll answer based on the conditional statement. And once again, this is a question that you can answer two ways. You can answer it by analysis or just by testing it with the properties tables. I personally think these property tables are a better resource than the professors actually think. Anyways, so we can think about this logically. Let's see. How much energy would it take to take okay. Okay, so first we're going to do this logically and rather intuitively. Let's start off with a PV diagram. I love these things. You know, once you learn how to do them, man, they just make so much sense. Alright, PV. High pressure, low pressure. This is going to be our T2. This is a higher temperature. This is 120. And this is T1. Okay, that's 100 degrees. Alright, so we know that our mass is 1 kilogram, and we're considering which one will take more energy. First we want to look at why is the temperature constant here? You know, why is it constant there? This whole time we're adding energy because it's going from being very well organized and very compressed and liquid to being a gas, a vapor, whatever you want to call it. Either way, much less organized, a whole lot more energy in it. Alright, and usually when you add energy to a system, especially thermal energy, it produces a temperature change. The temperature will increase. And at the same time, the pressure will also increase. But under this dome, it just all of a sudden goes flat, and all of a sudden goes constant. The same is true for a TV diagram. Okay? So we've got this temperature that's increasing. All of a sudden it hits this beginning of the conversion, basically from liquid to vapor, and it just it stops. It stops getting hotter. Even though we're putting energy into it, it just stops getting hotter. Okay. Why is that? Let's see. I'll say this is gonna be our T2. This is gonna be our T1. So this is the corresponding P2 and the corresponding P1. Alright. So why does it do that? Well, you're putting energy into it and it is converting. But that's not going into thermal energy. Okay. Sorry guys, I am really having a hard time of it. I will definitely be editing these videos before I put them anywhere. Alright, so the TV diagram is actually the one that's more important. I realized that after I did this. So, over here we've got the temperature, which has kind of stopped increasing. We're just adding heat, and it's not getting hotter, but it is transforming from a liquid to a vapor. Alright. Intuitively, we could say that this gap is bigger. There's more time spent into expanding the specific volume. There's more energy put into expanding the specific volume at this lower point because the dome is wider. So yes, it would take more energy to vaporize a certain mass of saturated liquid water at 100 because that's a lower temperature than at 120. In theory. That's what we're saying. So, we're not 100% sure. Let's go check our tables. Alright, so we've got, you remember the first problem? I was just constantly calling the enthalpy, the latent heat. That's because while I was working on this problem, the professor was like, "Oh yes, that's you're looking at totally the wrong thing," because I was looking at internal energy. She's like, "No, you want the latent heat, which is the enthalpy." I was like, "Okay." Well, this is the enthalpy at the lower limit, the enthalpy of fusion. This is the enthalpy at the higher limit, the enthalpy of vaporization, or the enthalpy of the gas. Alright, this HFG, and if you haven't noticed, I hope you have, is simply the difference between these two. And honestly, I correlate that with the size of the gap, the size of the solid line, the flat line here. Because everything that happens in this chart is happening between the two walls of that steam dome. This is all within the walls of the steam dome. This is the enthalpy at the lower limit. This is the enthalpy at the upper limit. So as we're going across that line, you know, this is showing how much enthalpy is put into making that line progress. Alright, this is actually a pressure determined table, not a temperature determined table, but we don't need to know specific values. We only need to know general trends. So we can just keep using this one. Let's look at this saturated temperature here, 28.96. Alright, so this is the latent heat, or the enthalpy needed for evaporation. It's right here, 2400 scale, roughly. Alright, that's pretty big. Let's scroll down just a bit and look at 116 degrees. Huge difference. But it should give us the same general trend. Well, this number is on the scale of 2200, much smaller. Well, not much, but smaller. And if you just look at the numbers in general, they're going down as your temperature is increasing. Alright, so this represents the gap between the liquid and the gas phases. So we want to know, is there more of a gap? Is there more energy required for a lower temperature than a higher temperature? And the answer is yes. It takes more energy at 100 degrees Celsius than it would at 120. Because on that graph, we've got the temperature increasing as it goes down, and we've got the latent heat, the enthalpy, the heat required to vaporize this is actually decreasing as you go to an increased temperature, and this thing is all flipped. Let's see. Let's just flip these over, invert them. This is the exact reverse of what this is what the table said. This is what I'm saying. This is the opposite of the tables, because it works better with the graph. As the temperature increases, did it? I knew I was going to do it. Again, this should be negative. This should be positive. This is greater value. This is a lesser value. As we go from here, there's a very, very large gap. Up to here, it's a very small gap. So, even though the temperature is lower, the energy required to cross this boundary is greater. Maybe not significantly, but it is greater.